So essentially, what we talked last time, we talked about with this input, with this multi-perception here, that you have input and you have multiple hidden layers and output of that. So this is a 3-layer neural nets, or classically, people referring to this type of model called multi-layer perceptron. And you have only one hidden layers of that. And then the parameters of the models here will be the connectivity between the input layer to the hidden layer, and also the connectivity from the hidden layer to the output layer. So there is also a bias term associated with each individual neurons throughout this network here. So these are the parameters referring to as W and B within the models of that. So the terminology is slightly different from what we used before. Previously, we used theta, right? We said theta, and theta null, theta zero, referring to the bias term. But in the context of the neural net, people more commonly use this terminology, the W referring to the connectivity here, and also B referring to the bias term. So these are the set of parameters we need to learn here. So overall there are many parameters here, because each individual neuron you have set of W. Overall you have many hidden neurons here. So in general, you have 2 sets of matrices. So one is from input to the hidden, and the second matrix will be from hidden to the output layer. So these are the parameters we learn. And so how do we learn those parameters? And in general, it follows the same framework we talked about previously. So the only difference now is that now in this case, we have more complex predictive models. But in general, the framework stays the same. Given the input here, we're able to produce the output. So this will be my y hat. So this is a prediction. And what we plan to do is going to compare this prediction to the actual values, to the target values, and then calculate the difference between them, and then construct a loss function to evaluate the difference between them. So that if it's regression, for instance, you can use MSE to calculate the difference between the two. And if it is classification, and then we can use a negative log likelihood or some other loss function. And for instance, let's think about this loss function here. Suppose we have a loss function here. And then next, what are we going to do is we need to update the parameters of the models here. So in the context of neural nets, people referring to this parameter as the weights here. So the connectivity weights between neurons. And those are the parameters of the model. And how do we update them? We're going to apply gradient descent methodology, just like what we did before. So and then a key step in implementing those gradient descent methodology is to calculate the gradient of the loss function with respect to parameters. So that's something we're going to talk about today. How do we do that? And last time we talked about this, how do we do this? Well, in this case here, you do have multiple, you have this, if you look at this architecture here, what do you have here? First of all, you have this linear combinations of the input here through this weight parameter. And after that, we apply a nonlinear activation function, and then that to generate this output of each individual hidden neurons. And after this, those output here will be transformed through the linear transformation here. And essentially, those hidden neurons are treated as the input to the neurons in the next layer. And then with combination through the weight parameters, and then apply nonlinear activation again. So you can think about it as kind of repeated applications of this linear transformation, nonlinear activation, linear transformation, nonlinear activation. But the function in the end turns out to be pretty complex, because we apply this transformation repeatedly, recursively. And then, so in the end, how do we calculate the gradient of the loss function with respect to the parameter of the model? And then we're going to apply the so-called chain rule. So that we kind of refresh some of the basics of with the calculus, how to calculate gradient with respect to individual parameters. So for instance, suppose I want to calculate gradient of loss function with respect to the f function. That's easy. We directly calculate loss with respect to f. But suppose I want to calculate gradient of j with respect to g. How do I do that? Well, I can apply the chain rule to calculate gradient of j with respect to f first, and then take the gradient of f with respect to g and take the product between these two here. And by follow this path. And similarly, we can calculate gradient of j with respect to h this way and following this path. And in general, what you can see here is this. Those gradient calculation follow this kind of red arrows here from the end to the beginning. So this is the opposite to the forward path in order to calculate these predictions here. And that this is referred to as the forward pass because go from the input to the output here. But in order to calculate gradient here, we actually go from the end to the beginning. So that is the reason we call it back propagation because its path is reverted. And let's take one specific example here. Suppose we're going to talk about this previous models here. We want to, it's very relatively simple model. We have input, we have one hidden layer, and this is the output here. And then we're going to construct a loss function with respect to the prediction here. And then we're going to calculate gradient of this loss function with respect to these two sets of weighted parameters. One is so-called W2 here, and we're referring to those weighted parameters as W1. And how do we do that? So let's look at this forward pass. The forward pass is this. First of all, we calculate loss functions. Suppose we use this MSE as a loss function here. So this is your target value, and this y hat is your prediction. So in this case here, we have two predictions, and you have k indexed by k here. So k goes from 1 to 2. You sum over them, you get the prediction, and that will be the squared loss. And then and this is loss here, and then this is the output layer here. Output layer goes from the input from the previous hidden layers of that. That's h, and h came from the input here. So the forward path you go from this way, from the bottom to the up here. And start with the x here, you calculate the hidden layer, and then from the hidden layer activity, you calculate the output. Once you calculate the prediction, once you have the prediction, and then you calculate the loss function. And that's called a forward pass. And then next, what we're going to demonstrate is how to calculate the gradient of the loss function with respect to two sets of parameters. One is this W2, and the second one is W1. So W1 here would be the connectivity weight from the input to the hidden layer. W2 would be connectivity from hidden layer to the output. So that's the reason you can see linear combinations of W with the H here. In here is W1 with X here. And that will be two sets of parameters that we need to calculate gradient. Now, how do we do that? Well, first what we do is calculate gradient of loss function with respect to W2 here. And then we realize that W2, how the loss function dependent W is mediated through this Y hat here, through the Y prediction. And you can think about what I can do here. I can calculate the loss function J with respect to Y hat first. And then we'll calculate the derivative of Y hat with respect to S. And then calculate the derivative of S with respect to W. And then follows a chain of events. And in the end, we take the product of these three derivatives. And that was demonstrated here. First, this is a derivative of a loss function with respect to Y hat. Next, we'll calculate derivative of Y hat with respect to these parameters here in this kind of simple notation. What this is referring to is the derivative of Y hat with respect to W2 here. Okay, and then the question is, how do we do that? Well, what we do is we're going to apply this chain rule here because we know that the dependence of W2 on the Y hat with respect to W2 is mediated through this Y and the S here. So I'm going to calculate first we'll calculate the derivative of this nonlinear activation function, essentially Y hat with respect to S. So that will be sigma prime here. So this will be derivative of this activation function. So next, I'm going to calculate derivative of S with respect to W, and that will be simply H terms here. So that's what you have H here. So that completes the entire path of calculating gradient with respect to W2. So next, so that's okay. I know the rules for updating the parameter of the W2 here, but still I don't know the parameter gradient with respect to W, so I need to continue that. So how can I do that? Well, what I can do here is this. So now you can see this. In terms of W1 here, how this W1 will impact this loss function here. So they are mediated through the through the Tj first, and then goes through the Hj. Hj goes through S here, Y hat and W. So in the forward path is this. Essentially, when I calculate gradient here, I can do backwards here, calculate gradient of J with respect to Y hat, right? And then take gradient of Y hat with respect to H here, and then gradient of H with respect to T and T with respect to X here. So going this backwards here. And fortunately, and this is the benefit of this backpropagation with this, I do not do this from the very beginning here. I do not need to calculate j respect to y hat and y hat respect to h and so on. Because in this step here, I have already calculated the gradient of the loss function with respect to y hat. In fact, I have already the gradient of j here with respect to s here. So I already have that. So I can start from this point, this previous point here. And then next, what I need to do is to calculate gradient of s with respect to h instead of W2 in the previous step here. That's the only thing what I need to do here. I'm going to start with that. And then next, follow back to there. So that you can see from here. So previous steps here stays the same. This will be gradient of the y hat here. So next would be gradient of y hat with respect to sk. So that's same thing as here. I have this gradient, the derivative of the activation function. So next, what I'm going to do here. So I'm going to calculate derivative s with respect to h. Well, so this is linear combination. So that would be derivative simply the W2 here. So that's the reason I have this W2 term. The remaining is this partial derivative of hj with respect to these parameters here. And now what I can do, I continue to apply the chain rule here. And that will be this relate to this activation function sigma here. So this will be sigma here. So this sigma came from this part of the sigma here. And next will be the partial derivative of tj with respect to wji here. And that will be the x here. And you can see that looks like complicated, but follows a chain of events here. And what we need to do is to go backwards here to see how these variables here might impact the final loss function. Its impact is mediated through a set of intermediate variables here through this path. I just need to keep track of these intermediate variables and then running those gradient calculation backwards, and I will do that. So that you demonstrate here. All right, so this is the idea, it's something called a backpropagation. And you can simplify the notation a little bit in such a way that I do not need to apply this calculation every time from the scratch. Instead, I can take advantage of some of the intermediate gradient information calculated from the previous step. For instance, it's more common to do is to keep track of this so-called error signals. So error signal is this variable associated with each individual neurons throughout the network. And that's called error signals. So error signal essentially captures most of the gradient calculation because, you can think about this, all the parameters in the models here and its impact. Suppose you make a perturbation on those parameters here. Its impact on the final loss function ought to be mediated through some hidden neurons because only hidden neurons send this output to these neurons in the next layers of that. So all has to mediate through that. So that's the reason, and more importantly, is keep track of those error signals here. And for instance, I keep track of this, define this error signal associated with this case unit here in the last layers of the network here. And then what I can do next is to based on this error signals here and recalculate the gradient of these guys here with respect to the second set of parameters here. And what I need to do is this, I can update these error signals here, and I'm going to assign error signals associated with all the hidden neurons here. How do I do that? Once I have this error signal associated with this output neurons here, and then I can update the error signals here through this transformation here. So these are a set of parameters I need to do here. And if you do that, then implementation becomes much easier. So in that case, what you do is this. First of all, you initialize the error signal at the output layers of the entire neural network. And then now I kind of backpropagate the error signals to calculate the error signals in the hidden layers. And then after I have the hidden layers, and then if I have multiple layers, I can do backpropagation in the previous layers repeatedly. So by doing that, in terms of error calculation, we're doing something very similar to the forward path. The only difference here is that when you do backward propagations here, and what you need to do is you need to take the transpose of this matrix here So instead of the forward pass, you simply say W times H. But now you have error signals here, you backprogram here. How do you do that? You take transpose of this W. That's one thing you need to take into consideration. Second consideration is that you have this nonlinear function. And then when you backprogram the gradient signal, you need to take a derivative of that. So that's kind of this part of that. You can think about this W2K here times W2KJ and sigma prime here. And this will be the error signals here now associated with this hidden neurons you have. So once you have this, and then the updated parameters becomes relatively easy. And then you can see from here, the B2 here is the error signal that I have. And then I backpropagate the error signals here, and then update the back error signals associated with the hidden neurons. And then after that, the gradient is simply the product between your error signals and those the input activities. So what I mean here is this. So now if I look at this weight parameter WKJ2 here, so this will be the connectivity from HJ to YK here. So this neurons between these two. And then the gradient of the loss function with respect to these guys here was simply the error signal WK2 that will be here, and then times HJ, the product between these two. And then in that sense, this rule here is very similar to what we've seen previously in the case of logistic regression and linear regression. So in terms of the gradient in the logistic regression or linear regression, always this, right? You have the residual times this sensitivity parameter. And in that case, is input. But now you can think about it here. So this HJ here can be viewed as an input to these neurons as well. So in that sense, it's very similar. And then those error signals here can be viewed as a generalizations of the residuals we have. So indeed, for the case of the MSE loss and then logistic regression, and this W2K is still in the end what turns out to be a residual, right? So think about this, because if I'm solving a regression problem, and typically I'm going to choose this nonlinear activation to be simply a linear function. So in that case, gradient is 1 here, so that disappears. And then you can think now this error signals here is simply the residual, the difference between prediction and the actual observation. So the gradient is this difference between the product between the residual and the input here. In this case is H. Now you go back to update these parameters here. So in this parameter is the connectivity between the input Xi and this hidden neuron HJ here. So now, because I'm going to update this residual error signals HJ here, so that will be W2K times this weight parameter W2 here, because the error is going to propagate here through this W here, and then I have to think about count this nonlinear activation here. So this product, these 3 terms here, will be the beta 1J here. And now, you know, to calculate the gradient respect to these weighted parameters here, again, I simply take the product between this error signal at HJ and the input Xi here. So that it show up in this case here. So that is called backpropagation algorithm. You can see that. So now we have very efficient way of implement these guys here. And now if you know the gradient calculation, and then you update them using gradient descent or the modern versions of a stochastic gradient descent. You learn parameter this way. All right. So let's show you an example here. So this is a relatively simple example and a simple regression example. It's called an M-cycle data set. It's a motorcycle, the accident, the test data set. Essentially, in this case here, what is trying to measure here is the y-axis here is this accelerations of the head, the helmet. And then the x-axis here is this time after impact. It's kind of used in an accident test case. So what is trying to model the relationship between acceleration and time after impact here. So the relationship here is the samples that show up in the red dots here. You can see relation is pretty complex here. You know, certainly you cannot fit that with the linear curves. And if you train a multi-layer perceptron with 2 layers and 1 input feature, because you only have 1 input here, And then, and if you choose 10 hidden units here, one output target. So that because you are predicting only one variables here. It's a relatively simple multi-layer perceptron. And with logistic activation function, linear for the output. And now you backpropagate them, train the model, and then the model is predicted curve is shown up in those black curves here. And as you can see, it fit relatively well on this data set if we use this kind of multi-layer perceptron as a model. So one thing I want to kind of interested in to point out is this activations of these hidden units. And this show up here. So these are show up the response of the hidden units will look something like here. And then we'll plot hidden units all together, stack it together here. Each one of them, because in this case, we have 10 hidden units here. Essentially, each one of them is more or less like a step function. And that is pretty consistent with what we talked about before, right? So the hidden neurons in the first layer, more or less like step function, a thresholding function. And then the output is essentially a combinations of this step function here. And that's what's shown up in here, essentially, right? Because this is the curves here, and you have this linear regimes here. It's pretty relatively simple to model, and then this part here. But now you have the transitions here. And when you have transitions here, the neural nets is trying to model them with multiple step functions here. And then in the end, you combine those multiple step functions, is able to model the transitions here. And that happens in this side. And then there's happened on this side here as well. And then and so on. And you can see that how these nonlinear features are combined together in the end to produce something is relatively complex. So that's in the neural nets model. So this shows you another example is based on the classification. So that's the example we mentioned previously on the Irish data classification examples. And you can build this multi-layer neural nets to do this. So in our case, you have and I only use two features here in this case, in this demos here. So you have 2 hidden units here, and then you have 10 hidden neurons, and then three output neurons here because we want to predict 3 different classes here. So the architecture of the model would be the nonlinear activation function would be logistic activation for neurons in the hidden layer, and the output here will be a softmax, as we did previously, just in the case of a multi-class classification. So in the end, if you train them, in fact, this didn't use a softmax here. So in this example here, we actually use MSE loss to train these models here. Essentially, I have sigmoid activation function for neurons in the output layers as well. And after that, I calculate MSE between the sigmoid output and these labels. And then you can train that this way, and we show that's possible. And if you do that, and this is this decision boundary predicted by this neural nets here. Now you can see now here the decision is not kind of a linear decision boundary anymore. You can see little curves of that, and that separates these 3 classes of data sets we have. So this is another example of that. So what I want to show you here, so now there's actually a very nice demo. I will show you that so you can play around to try to, and I will help you have a better understanding of the neural nets models. And it's very, very useful models I want to show you. So this is a model that is provided by this in this TensorFlow.org website here, and allows you to play with this deep learning models a little bit. I think it's kind of very helpful. Let me show you what this means here. Right. So this is a models here you can construct manually, and then we'll construct the neural nets yourself. So let's take a few examples here. In this case here, let's consider a few different training data sets. Suppose let's consider this type of training data sets here. So the input dimension is 2 here. The relatively simple input dimensions here. You have 2 features, x1 and x2 here. It's a binary classification. You have sets of blue dots, you have orange dots here, and then with different labels you have here. And now suppose I want to train a model to separate these 2 group of data sets. And that's relatively a simple problem, and we know how to solve it. Even if you use a linear classifier, you will be able to solve the problem. And suppose let's do that. Let's do a linear classifier to do this. So I'm going to construct a model, a linear classifier. So in this case here, I have 2 input here. 2 input. One is the x1, the other one is the x2 here. And then this is the output neurons here. There will be linear combinations of these 2 here. Suppose I'm going to apply a sigmoid function to separate these 2 here. and then that would be the classification problem I have here. So so now you can train this with this with gradient descent to solve this problem. And then now you can choose what type of a problem. This is a classification. You can choose the learning rate to do that. So that will be very classical logistical regression problem. And if you run that, and the model is very trained. You can see now the model can very quickly converge to an optimal solution. And in that case, you can clearly separate these two classes of data sets. So this is essentially a logistical regression model. And we showed previously. Well, so what I'm going to show here is to explain what was demonstrated in this pictures here. So what I demonstrated here is this. They show up, highlight what those neurons is trying to respond into. So in this case here is really a simple model, right? You have input here and you have output. This is logistic regression units here. It's linear combination of these two. And afterwards, I apply a sigmoid activation. So what this picture here showing you as the input here shows you what these neurons is responding to. So if I think in terms of neurons here, well, in this case here, because this guy here is simply the input X1 here, you can see this neurons here doesn't care about the input of X2. So because no matter what's your X2 here is always the same here. What that's should be expected because this neuron is simply an input of X1 here. Simply, this X2 here is the input of X2. That's where you can see the vertical difference here, but the vertical different, but horizontally they are uniform here because they are simply the input here, right? And I can highlight that if I put the mouse on top of these neurons here, we can show up in this side here as well. But now you look at this neuron here. So these neurons now is more interesting because this neuron receive a linear combination of this input here. So the overall, the activations of these neurons here, if you change X1, X2 here, will look something like this. Will look something like this guys here. Have a large activity in the top right corner here, a low activity in the bottom left corner here, and now clearly you have linear separation between them. So that is expected because we said that this neuron is linear combination of this. And afterwards, we apply a thresholding function. And even though it's not really threshold, it's sigmoid, but sigmoid looks like a softer versions of the thresholding function. So that is expected. You see the decays of the activity show up in this side here, right? So that is expected. And then what this model is simply say, well, if this is greater than half, I can classify this with blue, and otherwise I classify with red here, and clear decision boundary. And that's clearly consistent with what we have so far. Okay, so you understand what was shown up in these pictures here. So now let's try a few more complex examples here. And suppose, let's try these examples here. So this example now, this data sets are not linearly separable anymore. And you have this blue dots in the middle and orange dots in the surrounding regions of that. And as if simply if I try to have logistic regression units here, we're not going to be completely separate these two group of data sets here. Well, if you don't convince, let's run that. You can see that the model will converge to a solution. A solution will be more or less an arbitrary solution here, right? So now you have this neurons here came up with decision boundary thresholding function looks something like this, but it doesn't completely solve my problem here. So this is my decision boundary here. You have a yellow dots in this region. And these are all classified as blue regions here, but clearly those orange dots in the up corner here are all incorrectly labeled. So that you can see it doesn't do that. And you can see the loss function will look like in this case here. So overall, this algorithm converged, but the accuracy is not so high because the features are not sufficient to be able to classify them. Well, previously we said we can augment the features. So that we show up previously. Say I can introduce x1 to x1 squared. So if we use x1 squared, now you have squared features here, and x2 squared, so now square feature. Now if I combine those augmented features, I might be able to solve that. Let's check that. Well, indeed. So now I can solve this nonlinear the classification problem. The way I solve it is by introducing this type of nonlinear features, polynomial features here. So that's how do I solve it before. And then you can clearly now, you can see these neurons here now have this very only show high activity in surrounding regions and low activity in the middle of that. And by doing that, I can apply this the classifier with using these neurons here, achieve good decision boundaries. So that's all good. And that's this framework we talked about previously. But suppose I remove those nonlinear features here. I don't use them. But instead, how do I do that? Well, suppose I introduce hidden neurons here, and to hopefully to see if I can achieve a similar goal. So I'm going to first use a multi-layer perceptron. So in this case here, I have 3 layers here. So this is input, and this is a hidden neuron, and the output here I have only 1 because I only have 1 class labels of that. So I'm going to introduce multiple hidden neurons here. Suppose I use 5 here. I have 5 hidden neurons and 1 output neurons here. So this is the multi-layer perceptron we talk about. And let's try to train in these models here to solve classification with this type of data sets here to see if it can do that. So let's try it. I think I'm doing here now. This guy's here, all good. Or use sigmoid activation functions here, classification and so on. This is learning rate, you can change that. All right, let's try that. So the multi-layer perceptron now becomes the kind of, as I mentioned, that the learning is more challenging because this loss function is not convex function anymore. So the algorithm has to go over different multiple local optimal solutions. Hopefully in the end, try to identify the best solutions for that. So that's one key challenge of the models. So right now, the model converged solution here is not a great solution. It's more still, it looks like a linear decision boundaries. And as you can show up from this loss function here, training loss, it decreases here, but then quickly reach a plateau here because it does not progress anymore because now seems like going through this relatively linear decision boundary, but doesn't solve my problem here, even though I have 6 hidden neurons here. So that didn't solve my problem. Or how do I do that? Well, so what I think in this models here might be in the end might still be able to find a solution if I keep running. Maybe find it. Well, let's do this one here. I think alternatively, what I can do is this. Right now, I have the sigmoid here. I have the 1 output here, and I didn't solve my problem here. Let's say I try to add 1 more hidden layers. Let's try that. So I make the model more complex, and then to see if it helps me or not. So now I have 2 layers here. So they have 3 neurons in the first layer, 5 neurons in the first hidden layer, 3 neurons in the second hidden layers here, connected by these guys here. And let's try this model. The model somewhat stuck here. I didn't do very well. And then maybe let's see if I did initialization wrong here or some reason. Let's do here. Let's try a slightly larger learning rate here in the very beginning to see if that helps or not. Okay, let's try that one more time. So it looks like so in this case here, the training is done poorly. So test loss is not decreasing right now. So maybe my loss is too high. Let's try something smaller. So let me try a different activation functions here to see if that helps. Oh, so this, so you see I'm very lucky here. So what I did here is this, I changed this activation function from the sigmoid to the ReLU activation function here. With that, the model seems to be able to quickly converge to a solution. I think even if I reduce the number of hidden neurons, I might be still do that. Let's try this one here. So still go back to the multi-layer perception with only 5 neurons here. Let's retrain. Yeah, so that can do it. So you can see now this activation function is actually pretty important in this case here. Okay, so let me explain what does the model discover here, right? So in order to solve these more complex decision boundaries with red dots in the middle and orange dots surrounding, so it's certainly not linearly separable case. And how did this model do? So even in a simple multi-layer perception with only 1 hidden layers. So what this neuron is doing is this, and this is input here. So now look at this activations of the hidden neurons here. So they are all simple features, a threshold function, you can see that. But the threshold is along different directions, different orientations. Here are different locations of that, different intercept, different orientations. This is one threshold, another one's here. You can see different types of a simple threshold function. Next, what this model is doing is, by combining this simple threshold functions here, now you can achieve a slightly more complex function now. It's become a blobs here, a dots here. And then these are achieved by simply combining these 5 threshold functions here. In fact, mostly came from 1, 2, 3, 4 here. You can see weight here relatively thin here, which means relatively small here. So by doing that, now you're able to extract kind of more complex features. And that feature is sufficient for us to solve this classification problem. And now you can see how this was achieved in this way. And also, I just want to show you that this type of activation function choice of that seems to matter as well. So previously, I tried the sigmoid. It didn't do as well as this ReLU activation functions show up here. All right, so this is one example here. And let's check another examples here. So let's check this examples here. So this example is much more complex. So this example is this. It's kind of a spiral structure here, but these 2 type of data sets have this spiral intertwined with each other here. And now this type of a classification is not easy to solve anymore. And in fact, you can try to augment these features here. It doesn't help you. Doesn't help to solve that, because it's an augmented feature. You can see that it doesn't contain the sophistication of this type of nonlinear types of patterns through this type of simple polynomial or sinusoid function. It doesn't solve that. And let's try to see whether this neural nets can solve this problem here. So I just warn you that model is more complex here. And let's play around this here. Suppose I use the previous models here to see how this model can do. So you try to monitor the performance of the loss function here, especially in the training loss in this thin and gray curves here, it drops here. But now once it drops here, it's still decreasing, still learning something, still learning. All right, and then there's another drop here. But in general, what you observe here is this, right? So the model has a difficult time to learn a correct classifier. And then right now it's trying to generate a feature, a blob feature like this, right? It's like regions here, but now try to separate these 2. And but that although it looks like a complicated feature, but doesn't solve our problems here. And what you can see is from this type of loss function here, it decreased initially, but then it reached a plateau very soon. And which means now the model is stuck within those solutions here. It cannot improve anymore. So that is a bad sign here. Well, so okay, looks like this cannot do that. Let's try to increase the the complexity of the models here. So you can increase complexity by increase the number of hidden neurons here, or by increase the number of hidden layers here. So let's do that. I'm trying to do a quick solution, trying to make it slightly more complicated to see if I can do that. And of course, you can try it at home, right? All right, so now I have relatively more complex layer here with the 1, 2, 3, 4 hidden layers, 4 hidden layers here, the 4 neurons here, 6, 6, 4 here, relatively complex here. Let's see if I can solve using this type of models here. Let's try it. So I'm running that. So the model now certainly try to go to identify the better solution than previous solutions now. Doing very well, in fact, as a matter, I'm very impressed, doing very well now. In fact, it's almost done perfect prediction on the training data now. And you can see from the loss function here, the training loss now is very small now, almost perfect. In fact, right now, in terms of decision boundary, now reaches a perfect solution. Now you can see here, this is all blue regions and the orange regions of that. So right now, the classification accuracy is 100% on the training data set. And you can see from the loss function here as well. So, so that's impressive, very good, very quickly. But now let's look back here to check what those neurons are doing here. And this is something I want to highlight here. So, I have 4 layers here. Let's look at the first hidden layer. So that is the same as before, extract relatively simple features of thresholding functions here, right? But with different orientations, different cutoff here. So that is a simple thresholding features here. And now in the second hidden layer, now features become more complex now. Those features are constructed by combinations of this thresholding function here. So as a result, you can generate a kind of more complex feature look like this guy's here, this guy's here. More like blob structure, more complex structure here. And this is what happens in the second hidden layer. And now let's look at the third hidden layers here. So now the patterns become even more weird now. You have, here is more or less, still blob structure, but now you have patterns, kind of a very different type patterns. And now if you look at the last hidden layer here, now you have these patterns look something like this. Look at these guys here. And now this feature is very complex here. And that's what you learn from this neural nets. And that tells you a rough idea what these neural nets are doing, why they're powerful. The main reason why they are powerful is this. Through this different multi-layer representation, and the model is trying to extract more and more sophisticated features. The features are extracted kind of in a recursive way. Initially, it's relatively simple features. But then if you combine this simple feature, you construct slightly more complex features, like you can show up here. And now you can combine this, medium level complex features to be more sophisticated feature here. You can show up this guy here. Now this feature, you look at this feature here, more complex. And finally, you can extract extremely complex features. So this is actually the reason why these neural net deep models here are powerful is because by applying these things recursively, repeatedly, and then you have kind of very sophisticated representations of the input here. Initially it's x1, x2, but now I can represent x1 through this type of sophisticated patterns of that. And that explains why deep learning has become popular these days and underlying many of this state-of-the-art solutions to many problems, and because you can apply this different layers of representation. And right now I apply the 4 layers. But now imagine you can apply this with hundreds of layers, and how what kind of patterns this model can learn. That's more or less unlimited here, and that's indeed what people apply this type of thing to the images here. So instead of those simple 2 features, but if you apply to this very complex structured data such as images or languages here, in the end the features you learn here can be quite complex. All right, so that's the demo of the neural nets here. I just got a rough idea, you know, how this neural nets, why they are powerful, and how do you train these models. All right, so I'm going to say something regarding this. This is the classical neural nets, and you train with backpropagation here. I want to say something about this neural versions. The modern neural nets is something called convolutional neural nets here. And then the model I talked about previously is more commonly people are referring to as fully connected neural nets. The reason they are called fully connected is this. So each neuron in those models here receive input from all neurons in the previous layers. So that was showing up here. If you look at these neurons here, each one of them here, it receives connection from all the neurons in the previous layers here. And that's the reason the connectivity here is all to all. And even though the strengths learning here will be different later on, but there is a connectivity from each one here. They're all fully connected.